So I will only say a word about our emblem. It's you can't see it from distance, but it's a lion laying down, and it has a book in one hand and it has a sword in the other. And then it says in Latin, I think, ad utumque, which is supposed to mean prepared for both. And it means prepared to study and to use the sword. Because we have Danish people on the other side of the border. This is about something that happens to many metals. In some metals, it's formation of hydride, and in some metals the hydride disappear very quickly. In some metals they remain and cause a problem because the metal hydride is usually more like a ceramic material. It's very easily broken. And the interior of nuclear pressure vessels are more or less all of it is in zirconium, because zirconium lets the neutrons go through without interruption. But the problem is, of course, that it forms hydrides and then they fracture. So you construct something of a metal and you're happy with that. Suddenly you have a hydride instead, or a ceramic, and it breaks. And the thing is that the nominal concentration of hydrogen is not sufficient to make a hydride, but the hydrogen in the environment gets concentrated along close to crack tips and at cold spots, which I'm going to talk about here. You don't want to have a ceramic around the crack tip. A cold spot is created here in an experiment, and you can see the result here. This is the hydride, this outside is the zirconium. Here is the experiment with the specimen down here, and this is a code device that puts a small spot less than a millimeter on the surface of the zirconium. And here's another one. You can see cracks from the top. And these are called blisters because they bulge out of the material. And the volume increase is 20 volumetric percent, which means linear percent of 5, 6, 7 or so. And in Catania, maybe if you saw these pictures then, that was an analysis of the instabilities that occur at the surface. Now it's about the crack and the formation of the crack. And since it's expanding, you're expecting it to be under pressure. And it's a big surprise. It was then for instance, there has been a few accidents in Pickering in Ottawa. It's one of the accidents, and after that there was a lot of money spent on analysis. And as a surprise, they didn't understand why the crack came there, because there was no tension, it was compression instead, even if it's on the surface. And we did a different analysis of this and proved that there is actually tension, and that's what I'm going to end up with here. We do phase-field modeling. We did earlier spherical embedded hydrides, and we did that exactly. We got exact solutions. And now, when it's on the surface, of course, the temperature field surrounding the spot on the surface will be circular or spread circularly inwards. But also the stresses will interfere with the growth of the hydride, so it may assume a different shape. And you can see on the first page here that it's about 20–30% longer in this direction than downwards. So we wanted to use the phase field to keep track of where the material is. Now, in order to make a phase field analysis, you need a parameter that describes the material in the phases. And you need a parameter that is continuous between two limits. And one limit is the metal, the other limit for us here is the hydride. And then you can vary the state in between. But it's given by only one single parameter, which means that it has to be isotropic, which this material is not, that we are aware of. And here you see, this is the metal, and this is part of the hydride. So here, this psi is equal to 1, here is 0, and then it's continuously changing. So it's coming to a place here, and then it drastically moves upwards to become 1. And two things that are described by the phase parameter is the chemical potential. That tells you that you have minimum potential energy if you have pure metal or if you have pure hydride. And then in between there is a barrier, an energy barrier. And that's what you see here. This is the chemical potential. And it's low here where the metal is, and then there's a barrier against mixtures of the material, and then it's low here also, the pure hydride. And then it's the expansion that comes when you form the hydride. It's 0 when you have a metal, and it's 1 when you have the hydride. And if you put this all together and you put together the energy densities that are available in the material, so this is the free energy from the mechanical field, and it's the elastic energy, and this is the chemical potential that we saw on the previous slide, and here's a potential that has to do with diffusion, and it's the potential, it's the energy you get if you have two materials separated but without no walls in between. They will start to diffuse into each other, and then you can get back an energy that is of this magnitude. So then we use the gradient formalism to calculate the variation of F with respect to psi, and these equations are from Landau and Ginsberg, and their works in the 50s. And the variation is put together like this if you only have psi and gradients of psi. If you have second gradients, you get more terms. And then they say that you have this is a positive constant, and this becomes a driving force to create more hydride. Psi is increasing. This is a positive one. And then the statements are done like this. This is more or less for fun because we know what the equations will become at the end, but there will be a check of that. So we take the displacement in the same round, and then we get, after that, we get, of course, partial differential equations, and this is for psi up here, and this is for the displacement, and if you're familiar with it, you can see that this is Navier's equation, and these are the normal terms that you will get if you have swelling or if you have plastic strain. So Navier's equation, that's solved directly by any finite element program that you may have that can handle mechanics. And this equation, that is the equation for phase, happens to be an equation for diffusion or for heat transfer, Fick's law or Fourier's law, with source terms on the other side. And that is available in many finite element programs, and like Abacus is one of them that we're using. And it has a temperature displacement element that we can use because it's in total analogy with this. So then we say that this is just for heat exchange, transport of heat, and these are sources on the other side, and this is solved directly by the code without interference from us. We have to give the swelling only. And you see it's fully coupled because here's the elastic strain, and this term here is depending on size. So these two equations are coupled. And this is the result. First of all, I should say, this is the result for first just to test on a sphere, because on the sphere there is an analytical solution. And the solution is by us, by surprise. Because there is already a solution that is used a lot by people in material science, and that's the Eshelby solution for an expanding inclusion. And everyone knows that the expanding inclusion gets compressive stress inside, and it's homogeneous stress also. But this is not, and then you take a region, like a sphere, and then you have zero expansion, and you increase the expansion gradually until you have your final expansion. But that's totally different from our result, from our problem here. Because our problem starts with a very small inclusion, and it grows by including more and more material. And the expansion goes on at the surface all the time as the thing is growing. And because of plasticity, it's history dependent, and also because of its formation of the hydride, it also becomes history dependent. So instead of getting constant compression, Hill gave a solution for a spherical inclusion with compression. And this is according to Hill's solution. And here's the place where you have plasticity. Now the center of the hydride is here, and this is outwards. So plastic zone outside the hydride, and then a sudden drop with 2 times the yield stress down to the lower limit, and then it's constant inside the yield solution. If you acknowledge that this is actually growing layer by layer and follow the history of it, it will form a logarithmic singularity at the center instead. And a logarithmic singularity is a singularity, and if it's a tensile stress, then things ought to crack in there. But of course the model doesn't consider the cracking. So the analytical solution supposes that there is no crack. This goes up to infinity. And then this is done by using the phase field equations that we had, and the finite element solution for some reason drops a little bit below. I wonder what that is. I didn't reflect on it earlier until yesterday. And then it drops, and this curve here is when the hydride is small, because then the interface between the hydride and the zirconium is quite wide. And if it's smaller than the width of this interface, then it totally drops out and disappears. And that is what is called Ostwald ripening, if you're familiar with that. And then, as it grows, it comes closer and closer to so the last blue one is pretty close to the analytical solution. So we're happy with that, and then we did finite element calculations of the hydride on the surface of the specimen. And still we can see that there is this is the classical solution where all this blue here is expanded simultaneously, and this is when it has grown from being small and fully expanded and growing and growing and growing out to here. And then you can see that at least the principal stresses are decreased at the surface. And this is the ratio of the radius on the surface and the depth. And that was what we were trying to figure out, because the simulation that we did earlier was for a half sphere. And you see there are small differences, but not very much, some 10% or so. And here's the solution for stresses. And this is now, if you imagine the zirconium surface here, here's the blister, and this is along this axis downwards where the crack is. So the crack is expected over here, and this is inside the hydride. And we have more or less compressive stress here. And then it increases, and then you have the outside. But you see, if the yield stress is 0.5 at least, then we get tensile stress at the surface. And the next one is a calculation that we did. The first one was without the crack. This is with the crack, and we let the crack grow whenever there is tensile stress, which means that we consider the fracture toughness to be almost nothing of the hydride. And I didn't tell you that. The fracture toughness goes down from about 40 megapascal square meter to 2 or so in the hydride. So it's almost nothing. People who try to make blocks of zirconium hydride, they end up with gray because it doesn't stick together. So we just let the crack open up when there is tensile stress. And this is again in the middle of the hydride from the top surface, yes. And then we go down into the hydride downwards. And you see here, this is the displacements, the opening of the crack, and here it's intact. And the stresses are, because of the crack, then the stresses instead are 0 here. And this is for the plastic material, and the elastic material is like here and goes up here. A very tiny little crack. And the crack in the experiments are more like around here, so that's still a miss. Now, summary. Well, of course, the growing hydrides were examined by us using Taystill model now. And the expanding hydride develops internal tensile stress, at least in some of the cases, but we're not ready with that yet. Fracture could possibly be explained by that. After the pickering, they said there's no way the crack can come just by itself, so there has to be some vibrations or so, and they spent a lot of money on that. And it's a big surprise that no one thought of this alternative way of solving the stress state in a growing precipitate that is growing with full expansion all the way. But I said that now. I said that in a couple of papers, and I said that in a couple of conferences, and no one protests. But I will not be surprised if someone protests and have an idea or acknowledge something. Thank you very much.